the following. Yes, so the agenda is the following. So I will give a very quick overview of my research career since 2009. And then I will speak about solution theory for Riccati and the Lyapunov equations, with emphasis on the Riccati equations. I will introduce a context of stochastic control, and that will be the only stochastic analysis that you will see in this talk. And then I will introduce notation and setting, and some solution concepts and main results, and then I will give an overview of the proof. And usually I think it's more interesting with proofs than results. So also emphasis will be here, but I will abstract away uninteresting technicalities. So I think it will be, I hope it will be interesting for the mathematicians. Yes, so I started my PhD in 2009 and defended it in 2015. My research topic was stochastic PDEs, and my supervisor was Stig Larsson at the department. I was a postdoc for 15 months at the TU Berlin. Then I continued to work in industry as team leader and consultant at Syntronic Software Innovation. And I then 15 months again as a chief scientist and consultant at Smarter. And now I'm a radar system engineer at the Saab Surveillance here in Gothenburg. So as I said, I worked with stochastic partial differential equations and in particular weak error analysis. This is a typical weak error bound. That's usually the main result of parts of my publication list. And here X is a solution to stochastic PD. And this is a numerical approximation with the space discretization parameter H and time discretization parameter K. You can think about the finite element approximation. And we have this convergence rates. And this is usually quite hard and technical to prove. And therefore, quite a lot of my research has concerned solution theory for the actual solutions to prove existence and uniqueness, and also regularity results, and something which is called Malevin calculus. It's a differential calculus for random variables on suitable probability spaces. And I developed theory and tools and proof techniques for the weak error analysis using Malevin calculus. And then I've been working also on stochastic control, but no publication yet. It started in 2012, and it was actually an interest that started already in my master thesis work, which I've been working sort of in parallel all the time since then. And then from 2016, I started learning deep learning, applied to partial differential equations, stochastic control, nonlinear filtering, Bayesian methodology, and now after 5 months at Saab, I'm also interested in radar data and signal processing. Yes, and the research part here has been concerned most the supervision of 7 master thesis projects, resulting in no publication yet, but still I learned a lot. Yes, and then I made a visualization of my projects. I think it could be a bit interesting to see. I was very slow in the beginning of my PhD. So here I was on parental leave for 2 periods, but then it took like 2.5 years for my first publication. And I'm very thankful, looking back at it, that it was not problematized. I was feeling that I did a good job all the time. Then I started a lot of projects in the second part of my PhD, which is perhaps a bit odd, I don't know. And also the projects are quite long, and also the publication process. So it took 4.5 years to get this one accepted. It will be published in March next year. Yes, so that was about my background. So the project about Riccati equation is an ongoing work with Boal M. Jehice at the Royal Institute of Technology and Stig Larsson at Chalmers. The project about Lyapunov equation is on archive. It's a joint work with Annika Lang at Chalmers and Andreas Petersson at the University of Oslo, and Leander Schrö, who was my master's student at TU Berlin. Yes. So the context is that we consider this control problem. It's a quadratic, cost functional of this form, and a linear state space or state equation. So you could think about X to be a vector valued like in Euclidean space, and A and B, so be matrices. Then this is very well covered in the literature. In this case, X takes value in a Hilbert space, and A is an unbounded operator, like for instance, minus the Laplace operator, and B operator, bounded or unbounded. And the control or the noise here is linear in both the state X and the control U. And W1 and W2 are so-called cylindrical Wiener processes, which are independent. The typical setting is the heat flow in a domain with sufficiently regular boundary. Distributed control, that means that B is bounded. Could take the identity, for instance, then the control enters the system in the interior of the domain, if that's the setting that we consider. Or it could be Neumann boundary control. Then U is the Neumann boundary conditions, and B is an unbounded operator, which maps the boundary conditions to the solution or to the equation. Or it could be Dirichlet boundary control, which is another operator B, which is more severely unbounded. And as I said, linear multiplicative noise. You could think about, the way I think about it is that if we want to control the system here, then we add a disturbance to the system here, because I don't think you can control really the system with this term, because the noise sort of say don't have a direction. Yes. And then we also have observation here. We have different Hilbert spaces, D and U and W and so on. It's because we want to have a flexibility to either work in the interior or on the boundary. And here Q can be unbounded, G can be unbounded, or it can even be regularizing, and so a compact operator, which is needed in the case of Dirichlet boundary control, for instance. Then you need a regularizing terminal cost operator G. The optimal control of this problem is given in this form, and here I have to explain what E and P and X is. And E is given in this form, so it's the operator inverse of a sum of two operators, where the argument L here comes into the middle. Here is the Riccati equation, and here is the optimal dynamics. So before we had an arbitrary U, but now we have the optimal U. Yes. So motivation for the work. It's the first result in the literature to include non-trace class noise. So we can, for instance, have a space-time white noise here. It's the first result in literature, or it will be the first result in literature to rigorously include the case D not equal to 0. There is one paper, which I will explain a little bit more about later, that considers this, but there is an error in the proof, so it contains a gap. It expands a variety of applications. So I parameterize the operators, and these parameters can be chosen to fit different applied problems. And I prove, or will prove, regularity results that allow error analysis for numerical methods. That's the main reason for starting this project, to build a theory that that considers a setting that we consider interesting, and also prove the regularity bounds that are more detailed than the one previously proved in the theory or in the literature. I would say that the topic was active from 1972 to 1993 when it comes to Riccati equation for deterministic control. Main contributors were Balakrishnan, Curtin, Pritchard, Franco Flandoli, Lasieca, Tragiani. Ishikawa was the first in 1979 to consider stochastic control. And Franco Flandoli was sort of the main researcher in this topic from 1982 to 1993. And I would say that there is no essential contributions from 1993. So it's sort of a dead research topic, but what was proven was not useful for numerical analysis. And that's the motivation for this project. This paper is mostly related to these three papers. So the setting is most similar to this paper, but that's the paper with which actually have an error in it. The analysis is perhaps most similar to this paper, and I use some inspiration in one of the theorems, and from this paper I pick some operator theory. So now to the setting. So there will be some slides with quite some notation and setting, and I will explain what you have to remember. So for two Hilbert spaces U and V, we let L of UV be the space of boundary linear operators. When U equal V, we write L of U. Sigma of U is the subspace of all self-adjoint operators. That will be important. Sigma plus is the closed cone of all self-adjoint positive operators. L2 is the subspace of all Hilbert-Schmidt operators. And then we have spaces of strongly continuous functions. So strongly continuous functions from 0 to tau being operators. We denote like this, and strongly continuous means that it's continuous when you let a vector act on it, not as an operator. And when we remove the initial time, we allow singularities, and we code the singularities by parameter theta, and we introduce norms on these spaces. And here is the Hilbert spaces for the Riccati equation. So it's H, U, V, W, H1, H2. It's only H that is interesting for the rest of the talk. These are introduced for the flexibility to consider interior or the boundary, and these are introduced for the noise. A is an unbounded operator with the domain A. It's positive, and minus A is the generator of an analytic semigroup that we denote by S of T. H of R are spaces of fractional powers with respect to A with this norm. And here we introduce positive self-adjoint operators with some additional regularity. And with if theta is in this space, then this property holds. And remember that A is an unbounded operator, so this means that in order for this to be finite, theta must have some extra regularity. And for mu and nu, the norm on this space is given by this. And also it's an analytic semigroup, so we can use these estimates that gives a singularity and also a sort of Hölder continuity result. But any technical computation concerning singularities will be abstracted away in this lecture. You will not. I will spare you that. So here is the spaces and operators, or operators. So we have parameters alpha, beta, gamma, delta, and rho. B is again the boundary operator or the control operator. So, and alpha codes the regularity. So alpha equal to 0 corresponds to distributed control in the interior. Alpha equal to 1/4 plus epsilon is Neumann boundary control, and alpha equal to 3/4 plus epsilon is Dirichlet boundary control. C and D are the operators for the noise. So they map linearly into a space of Hilbert-Schmidt operators, and beta here is a regularity parameter where beta equal to 0 correspond to trace glass noise, and beta equal to 1/4 plus minus epsilon, I don't remember which is space-time white noise. G is the terminal cost operator. It will also come into the initial value of the Riccati equation, and we have this regularity parameter gamma, and delta controls the regularity of the observation operator. R is the control operator, it's bounded. E, we define this function E now properly with the suitable spaces. We require some extra regularity of this input argument in order for it to be defined. And we define it on the positive operators, and for positive operator, the spectrum of this operator will be bounded away from 0, and therefore the inverse is defined. So now to solution concept. A function P is called a mild solution. So it's positive and self-adjoint, and it's strongly continuous into the space where the initial value has its regularity. The restriction to the semi-open interval 0 to t belongs to has singularities when measured in stronger norms, and the singularities are given here. And for all t and x, this equation holds, and it's an integrated Riccati equation. You can think about S as an integrating factor, but here we have the semigroup acting from both sides, and also X is, it's important that X is inside the integral, because if we would move X outside the integral, then the integrand would not be Bochner integrable, so the integral would not be defined. And a variational solution, so the 1 and 2 are the same. Here we explicitly have to say what the initial value is. This map has to be continuously differentiable for x and y in the domain of A, and for all t and x in the domain y in the domain of A, this equation holds. And I will not say anything more about numerics, but of course, if you would do finite element methods and so on, this is the starting point when you want to derive your schemes. So one slide about the main results. There exist unique mild solutions to the Riccati equation, and the solution is non-negative. A mapping P is a mild solution if and only if it's a variational solution. And then the regularity that I talked about before. So here it's more precise bounds. So if we have consider various regularity with θ1 and θ2, then we get the bound that, or we get the correct singularity. And that is very important in error analysis. And we also have a Hölder continuity result with operators, with various regularity also. So now to the proof, and the proof will be based on 2 applications of Banach's fixed point theorem. So I will recall this for you. So we let U be Banach space and let phi be a contraction. And being a contraction means that there is a small number C, and such that for all U1 and U2 and U, this holds. So it should be Lipschitz continuous with Lipschitz constant greater than 0 and less than 1. And under the given condition, there exists U, X in U, such that satisfies this fixed point equation. And in practice, You fix a suitable Banach space for your problem. You prove that the fixed point map is well defined. That means that if you start with U, then it will map into U. That's not obvious. You have to prove that, and you prove that you prove the contraction property. And here you usually have some choices. If you want, there is a uniqueness statement here, and if you want to prove uniqueness, it's good to have a big space because that will give you a stronger uniqueness result. Because if you prove uniqueness in a small, tiny space, then you might ask about solutions outside this space. But on the other side, you can define stronger norms that gives you additional regularity results for the solution. So it's a trade-off between regularity and uniqueness. Okay, so now to the proof. So I define a family of Banach spaces, B tau, with the properties of being a mild solution, essentially. So it was an intersection of three spaces. And we define this norm, so it more clearly explains what we require of a solution. It should be bounded with when we have a to the gamma on both sides. It's allowed to have singularity when we have a to the alpha, and it's allowed to have another singularity when we have a to the beta on both sides. And we define non-negative restrictions to this space, so we take all the intersection with all non-negative mappings. So that these spaces will be important. And to define the fixed point map, we have one map for the initial value. Here theta is acts as the initial value, and I have a map I epsilon will be my notation for a solution before I have a global solution, and psi, and here I let psi act on E here, and epsilon acts on the rest of the places in the integral where we have the solution. And when epsilon equal to psi, we write I of psi. So the fixed point problem is to find a unique P in V plus T such that this holds. But there are two complications. One is that if we would look at this map, this fixed point problem on the non-negative restriction, then it will not map into the non-negative restriction because of this minus sign. It is well known and expected that the solution itself will be non-negative, but the map itself will not respect this property. So that's not an option. Another complication is that, okay, let's relax and remove the non-negativity, but then this map will not be defined because we cannot guarantee that the spectrum of this operator is not zero, does not contain zero. So the first attain. Okay, so let's proceed with something else. And this is an attempt that failed, but I still think it's interesting. So we instead consider an equation where we put the absolute value here. And absolute value for an operator means that you take the square root of the operator adjoint multiplied by itself. And because then that fixed point map is well defined on V tau. But is it a contraction? If it is, then there exists a unique solution. And if we, in a second step, can prove that it's non-negative, then we also know that epsilon is equal to its absolute value, and therefore it solves the original equation. So what's the problem here? Is this map globally Lipschitz continuous? So I was stuck on that for a few days in my work, I tried to prove it, and the analysis simply didn't suggest that any natural way to prove global ellipsis continuity. So finally I asked Andreas Rosén at the department, and he pointed me to a paper by Cato from 1973 that said that no, it is only local Lipschitz continuous, and here is the local Lipschitz bound that then tends to infinity as S1 and S2 approaches the other. So that attempt failed. And actually this paper that considers D not equal to 0 relies on the above technique and therefore contains a gap. So a successful second attempt is to, so first of all we look for a local solution. That means that we look for a sufficiently small tau, because we cannot get a solution on the entire time interval directly. Then we let theta be our initial value, and we fix psi, and we prove for fixed psi and theta a solution to this problem by proving by using Banach's fixed point theory. And in a second step, so here we let upsilon tilde be the solution map that maps theta and psi to upsilon. So if we can prove that there's a fixed point upsilon to that map, then it means that psi and upsilon will coincide, and that solves the original equation. So this is a quite long and technical road to prove this, but it gives us all the regularity results that we need. And this is also a quite technical and long path that requires that that upsilon tilde is well defined on from V tau plus to itself. So you require non-negativity, and that I will explain to you how to do that. So the first step is to prove the equivalence of mild and variation of solution to the auxiliary problem. Once we have the global solution, later we can apply it directly, and it will apply for the true global solution. And then we prove under very strong assumptions either of the following two. So there's two paths leading to positivity. One is to prove a stochastic representation that the quadratic form generated by the solution is an expected value. That's essentially the cost function for the control problem. There's a stochastic PD involving the fixed psi and so on in here. I will spare you the details. Or you prove that there exists a strong evolution operator that's almost like the semigroup generated by, so the semigroup was generated by minus A, and the strong evolution operator is generated with this perturbation. And in that case, the minus sign in here becomes a positive sign, a plus, when we use U as semigroup, so to say. And that gives positivity under very strong assumptions. And then we take a limit of non-negative operators. And the limit of non-negative operators is non-negative. So that's that proof. But now we have solutions for small tau. And then we iterate this. So we start with, we get a local solution with a correct initial value. And then we take P1 is equal to the endpoint of P0 and so on, and iterate to the final time. And the mild solution, you can put it together this way. So it's, yeah. But you need to be very careful here, because it might be that when you do this iteration, that the tau that is allowed that you prove existence and uniqueness for might go to 0 when you do this iteration, and you will never end up at the final time. So therefore, it's classical in this kind of analysis to prove an a priori bound that says that if epsilon solves this equation, then there exists some constant kappa here that such that the solution is bounded by kappa, and epsilon here, or no, tau, the time that we can prove local existence and uniqueness depends on this norm. So this a priori bound says that gives that we can proceed in a finite number of steps and go to the terminal and reach the terminal time. And I think the key idea to the proof is interesting. We have now proven positivity of epsilon, and we also know, therefore, that also this is positive and theta is positive, so we can take the square root of that. And then if we take the scalar product, the quadratic form of epsilon, then we can take the square root of, say, epsilon here, and we get the norm squared, but with the square root instead of epsilon itself. And you can do the same thing with every of the term. And here we get positive terms and minus a negative term. So therefore, in the analysis, we can simply remove it. So when you work with equations with non-global ellipses, continuous non-linearities, you have to do something in order for, you have to use some structure from the problem to get rid of or to prove this kind of bounds. And for the Riccati equation, it's simply this minus sign that allows us to do analysis or to prove the a priori bound. It could be for other equations that use some monotonicity conditions or some other structure that you have assumed about your equation. Yes. And then this is a standard Gronwall argument then after this. And this proof was, it's found in the literature in the case when for deterministic equations where c equal to 0. So in that case, Gronwall's lemma is not needed because it's simply this term is 0 and there's no dependence on the solution on the right-hand side. Yes, and then my final slide is a comparison with the Lyapunov equation. So the Lyapunov equation is the linear Riccati equation. That's the case when b is equal to 0. So there is no quadratic term in the equation. And I just want to compare the existence and uniqueness proof, because here, when you have an equation which is which either is linear or it has a nonlinearity that is global ellipses, then you don't need to do a global, or you don't need to find a local solution. You can find the global solution immediately if you choose your norms in a good way. So we define a family of equivalent norms where we have an exponential here, e to the minus theta t, in both parts of the norms. And then we prove that is well defined. And for sufficiently large theta, the map I is a contraction. So this is something I've used not only in this project, but in other projects. It's also possible to prove local uniqueness and then put the pieces together. But I think this is more elegant and something you should try if you attempt these kind of problems when there's not when the nonlinearity is non-global Lipschitz. So that was everything. So thanks for your attention.